This is lecture number 22, and it's the second last presentation that I have for you this semester. And it will deal with the following items. So that's on the agenda for today.
As for ISO standards, ISO stands for International Standardization Organization, or some people call it International Organization for Standards, and they set the certain guidelines for vibration levels for different from different sources. Uh, Vibration is often undesirable. However, I mean, there are situations where we do want to intentionally introduce vibration into the system. For example, the phone the phone that goes on the vibrator, or in order to sort things such as bolts and coins and some vegetables, etc. They use a shaker table by making things of different sizes go through different holes, but this has to be done continuously by shaking the surface of the table or the container. But generally speaking, vibration is undesirable. For example, passenger discomfort due to fatigue in a while in a car which is going over a bumpy road. Now, every device that is used for military applications must meet the mil specs, which is specification set by the military, and this is regardless of the amount of vibration it can withstand. If a device does not meet those specifications, either mil specs or any other standards set by other organizations, they have to be redesigned, irrespective of whether they are for military or civilian applications. Now, redesigning or in general design is not a straightforward and very uh, easy thing to do, because first of all, when you design, there may be many different solutions, and obviously, depending on your needs, you have to take the one that meets your needs or is optimal. Or and it's not as and it's not does not have a unique solution, and it's an iterative process. This is why designing products is not as easy as it sounds. Now, in this lecture, we will focus the design when it refers to adjusting system physical parameters to cause its vibration response to behave in a very systematic and desired fashion. So obviously, you must have a fairly good idea of what is desirable, what are the criteria that our designs must need. And this brings us to the concept of acceptable levels of vibration. Uh, Well, to design a device in terms of its vibration response, the response must be clearly stated and defined. Cannot be a wishy-washy statement. You have to, in a very precise way, decide what is it that needs to be achieved. Uh, these are some specs that are taken from your Inman book. For example, when it comes to different systems, the frequency ranges are different, ballpark figures are different, and the displacement amplitudes are different, for example. In the case of atomic vibration, in chemistry and material science, etc., the frequency of vibration of the atoms is of the order of 10 to the 12 hertz. That's a huge number. Okay, and the displacement amplitude, because of the nature, the size of the atom and everything, is extremely small. It's roughly 10 to the minus 7 millimeter. It isn't that ballpark figure. For human perception, the frequency range is 1 to 8. We can perceive things as long as as long as it's in that range, and the displacement amplitude is of the order of 10 to the minus 2 millimeters. So that is 0.01 millimeter, something of that order of magnitude. For machinery, the frequency range is somewhere between 10 and 100, or 10 and 1,000, for example. And the amount of displacement is of the order of millimeter to centimeter, something of that order of magnitude. Uh, right. And for tall buildings or tall structures, the frequency range is between 1 and 5 hertz, and the amplitude of displacement, it can go as much as a meter. So this gives you a ballpark figure of the range of frequency and displacement during vibration. Now, certain standards were set by ISO, and it's under the ISO 2372 designation. And we're going to be looking at those in a few minutes. And this is intended for facilitating communications between manufacturers and customers. Okay. Now, those standards, most standards are in terms of the RMS values. Okay, so of course, things can be thought of in terms of the peak values, the maximum, for example, values, but RMS is very common, and that is what we're going to be doing our examples with. Now, let me remind you what the RMS means, XRMS means. If you have a signal X of t which varies with time, and if you integrate it from 0 to t, some big T, and then average it out by dividing by 1t, and then taking t to be bigger and bigger and bigger, assuming that this thing approaches a number, when you take the square root of it, you get the XRMS. Now, in the case of a special signal, a harmonic signal, actually, this is a very simple expression. You don't have to go from 0 to t as t goes to infinity. All you need to do is to integrate it over a single period, where t is the period, and then divide it by 1 over t, okay, or divided by t, and take its square root. We'll get that. Now, one of the important tools in uh, vibration analysis is the concept of nomograph, or what is called by civil engineering a tripartite plot. Now, this is a log-log plot, and it requires some explanation of what exactly it is. First of all, it's a log-log plot. It's for a single degree of freedom and a harmonic loading. So just remember, these are the limitations of, or limitations of the nomograph plot. So we're dealing with a single degree of freedom system which goes through a harmonic motion, and it gives you basically, it deals with the RMS values of displacement, velocity, and acceleration uh, as a function of frequency. And of course, you'll see that once you have one of these, you have the other two. Once you have, for example, displacement, you have velocity and acceleration. Or when you have velocity, you have the other two, displacement, acceleration. So let's move on. Now, we will see this, but it requires an explanation. It's not as straightforward of saying, yeah, here's the plot, and that's what I'm going to be doing. So what is the idea behind the monograph? Not monograph, nomograph. So easy to. So if you have a harmonic signal, sinusoidal signal with a frequency omega n and amplitude x, basically we have a statement on the top. That's how x is going to change with time. Now, the peak amplitude is big X. The RMS amplitude is 0.707x, okay, 0.707x. Actually, if you do that integration over one period and work it out, you see that you get 0.707x. The velocity, in other words, if I take this and differentiate it and use that formula, you see that you're going to get the uh, VRMS, which is going to be just the thing up there, just the thing up there multiplied by omega n. That doesn't surprise you, because if I was talking about peak X peak, X max, that'll be big X. If I differentiate this thing and I talk about peak velocity, because when you differentiate sign, you get omega n in the front, it's going to be omega nx, okay? However, we're not talking about peak value, we're talking about RMS. So whatever x RMS is, which is right here, you multiply it by omega n, you get the peak velocity. And one more time, you differentiate this thing again, you get another omega n. So RMS acceleration is the velocity RMS times omega n. Or in terms of the XRMS, that'll be XRMS times omega n squared. Okay, so these are obvious things. So what I've done here, I've written these last two. Instead of x dot, I've written it as VRMS equal to XRMS times omega n, and acceleration RMS is equal to velocity RMS times omega n. So I've repeated these two lines here without the x dot and x double dot. Now, since we're interested in things not in terms of omega n, but in terms of frequency in hertz, I've written omega n as 2 pi fn. So this says exactly the same thing on the top, except that omega n is in radian per second, and written in hertz is going to be 2 pi fn. And the same thing down here, this omega n for acceleration is written as 2 pi fn. Now, if I take these last two equations and take log of both sides, so log of v is equal to log of x plus log of 2 pi fn. And the same thing with the second one, log of acceleration equal to log of vrms plus log of 2 pi fn. This is the property of logarithm. And if I rearrange these, in other words, for the first equation, I just wrote it up here. You see that? The second equation, I actually took log v to the left side and log to the right side. So I'm sorry, I took log of 2 pi fn to the left side. So there will be a coefficient of minus hang in there. This, yeah, that's good. That's very good. That's exactly what I want. Yeah. So I've taken this log to the left side. So we have log of v equal to negative log of 2 pi fn plus, of course, log of arms. Now, if you look at this top equation, the very top equation, if you gave me xRMS, I know the first term here. If you specified what xRMS is here as a number, okay, as a number, I know what this thing is, okay? And if I look at log of v versus log of fn, or 2 pi fn, this is a linear function. So log of v is equal to 1 times log of 2 pi fn plus a constant. In other words, log VRMS varies linearly with frequency, log of frequency, with a slope of +1. In other words, if you gave me XRMS, a constant number, and I plotted log of V versus log of Fn, yes, I left out this 2 pi here because that 2 pi doesn't do anything, basically. You get a straight line with a slope of +1. And if I look at the second equation, log of velocity is equal to minus log of the frequency plus a constant. If you give me ARMS, if you give me the acceleration, I can say log of V is equal to negative log of Fn plus a constant. In other words, it's a line with a slope of -1. So this is the idea behind that nomograph plot. And we'll see that in a minute. In other words, it's the fact that for a given XRMS, for a given amplitude, variation of log of V versus log of Fn is going to be a straight line with angle 45 degrees. And for a given acceleration, the plot of log of V versus log of Fn is a straight line with a slope of -1. Okay. So here is a typical nomograph plot, okay? And remember that this horizontal axis is logarithm fn, so it's a log plot. This is logarithmic axis for frequency. This is the logarithmic axis for velocity, vrms. So log plot, or log of v versus log of fn, okay? And notice that if you fixed a displacement, these are different levels of displacement. See that? These are different displacement. If you fixed one, the variation of log of v versus log of frequency is just a straight line. These are the accelerations. These are the accelerations, 1,000, 2,000, 4,000, 8,000, etc., meter per second squared. If you gave me one, if you fixed one acceleration, the variation of log of v versus log of fn is a straight line with a slope of -1. That's exactly what this thing is saying. I'm using RMS here, but as I said, everything can be in terms of peaks, for example. Now, you may feel that there is a need to review your log plots or semi-log plot. I suggest that you go to a very basic tutorial. These two are pretty good, and you can review it. For us, it's just going to eyeball. We're going to eyeball and come up with the numbers, but there's a systematic way, and if you want, you can go to these sites. Now, let's look at a simple example. It says, assume that an acceptable range of vibration for a device are between 2 and 8 hertz. So we know that this is the line 2 hertz, this is the line 8 hertz. We know that an acceptable level of vibration for a certain device is in this range, okay? And if the RMS desired acceleration is 9,800 millimeter per second squared in that frequency range. So as soon as we say that, it means that the acceleration must be below that. So look at the line. These are the line. These one with a slope of -1 are logs or acceleration. So find the line which corresponds to 9,800. 800. So anything below this to the left of it is acceptable. So right now we are between 2 and 8 and below 9,800 millimeter per second squared. Okay. And the RMS acceptable is 400 for velocity is 400 millimeter per second. So these horizontal line, this is 400. This horizontal line limits the velocity. So you must be below 400 to the left of 9,800 and between these two vertical lines. So this is an acceptable region for that device, okay, based on the specifications that's given. Now, I wrote these things down for your reference again. We already saw that, but there I use the big X here. Big X here, I'm putting the A, so it doesn't matter. You have seen it already. Now, if you look at, generally speaking, depending on the type of equipment that you have, the frequency ranges of concern, or remember that table that I gave you, are different. For example, for structures, for atomic vibration, etc. And uh, these, for atomic level or small, very small micrometer type uh, uh, displacement amplitude measurements, these are harder to do. And for tall buildings, of course, we can see it easily. Uh, Now, human perception is between 1 and 8. Okay, so we can perceive vibrations between 1 and 8, and we are more concerned as human beings. We are more concerned, or we are more conscious of the acceleration rather than the displacement. Okay, it is it that is, for example, the reason that why a 30 hertz oscillation in a car which is traveling at that acceleration is actually uncomfortable. Okay? It's outside of that frequency range, and this may be okay, but outside of that frequency range at this acceleration, you may feel comfortable in the long term. So here is actually this is the same nomograph that I showed you before, except that the standards set by ISO are set here. So these are the 45-degree lines. We show the displacement. These are the minus 45-degree line, which are the acceleration. And vertical axis is the logarithm of velocity, and horizontal axis is logarithm of frequency. Remember, these are log, plot. All of these are log. Now, if you look at the ISO 3372 standard for machinery, it's over here. In other words, it says that the frequency range is between 10 and 1,000. And if your velocity, for example, if your velocity is between this value and this value, basically you're in this range, you're dealing with a good good characteristic of the vibration of the machine. If you are between these two lines, it's satisfactory. If it's between these two lines, the velocity is between these two lines, it's un, unsatisfactory, and above that, it's just not possible. It's destructive, basically. Now, the other standard is for tall building, which is right here. Okay, this is ISO DP 4866. So basically, it says that if you are below this line, below the screen line, the vibration, there's no damage. Between these two lines, okay, between these two lines, and these are uh, uh, between these two lines, the cracks in the wall appear, and between these two lines, wall damage. There's a problem with wall damage, and finally, above that line is completely destructive. Okay, okay, and finally, for the human being, it's this blue area that you're talking about, or blue lines that you're talking about. So you can see that this one below it, we can't even feel the vibration. Between this line and that line, we can feel it, but we can feel it. And above that, of course, is totally unacceptable and is painful in the long run. Okay? Now, this same plot is reproduced here for you. The sources are different. The previous one was from Inman's book. This is from Rao's book. Okay, so it's the same kind of stuff. You can see that there is the ISO 2372 standard for machinery. There is the ISO standard 4866 for buildings, actually right here, sorry, right there. And finally, these two lines, this one and that one is for human sensitivity to vibration. Okay, same. So this is for machinery, that is for structures, and this is for human perception. So let's do an example. Suppose we have a car whose mass is 1,000 kilogram and stiffness of the suspension is 400,000 Newton per meter. Now, it hits a bump of 0.1 millimeter. Now, when I say, well, let's assume that this is actually the RMS amplitude, okay? It could be the peak amplitude, but we're saying suppose that it's the RMS value of displacement. So, of course, once it hits the bump, then the car goes over it or goes on it and starts vibrating up and down. It says, what velocity and acceleration corresponds to this vibration? Okay, in other words, if this is the RMS displacement, what are the RMS values for velocity and acceleration? And then there's a second question is, what can we do so that actually things get better? Basically, we don't even feel the hitting of the bomb and that vibration. Okay, so I'm going to do it on the next slide. The first thing that you realize is that uh, this graph is reproduced here because we have to use this human sensitivity region. First of all, you're told that we are dealing with single degree of freedom because this whole concept of nomograph and this tripartite plot is based on a single degree of freedom assumption. So we're given the K was given as 400,000 and M was given as 1,000, I believe, 1,000 kilogram. So you work it out and convert it to hertz is going to be 3.18 hertz. So essentially, the passenger in that car is dealing with a frequency of vibration of 3.18 hertz. Now, and the displacement, RMS displacement amplitude, RMS displacement is zero point 0.1 millimeter, which is, if you multiply this thing by 10 to the, convert it into meters and write in terms of micrometer, it's going to be 100 micrometers. So what happens is that here is the 3.18 hertz. That's this number. You go up, 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 up until you hit that curve, given displacement. We are given the displacement of 0.1 millimeter RMS or 100 micrometers. So that's this line. See that? This line, 100 micrometer, and it hits that line at this location. And this location falls actually in that range, in other words, between these two curves. So yes, it's perceivable, but in the long run, it could be fatiguing. Okay. Now, all of these can be found from the formulas that I gave you before. In other words, if this is the RMS value multiplied by omega n, you get 2 millimeters per second. That's going to be the value of the velocity. That's going to be the value of the velocity. It should be so. If you go horizontally, you should be hitting 2, and it hits the line at 45 degrees, sits on that line at 45 degrees, which is this acceleration. Okay, this line, the line through this, that line, not horizontal, the line at 45 degree with a negative slope like that is going to be corresponding to acceleration of 0.04 meter per second. But the bottom line is that you are between these two, and therefore it's reasonable, no problem. Both are within acceptable levels. Now, the question becomes, what if we try to move this point of intersection to the left? How do we do that? How do we move it to the left? That actually the passenger, it falls either on the line or below that blue line here. How do we do that? Because then the passenger does not even perceive, does not even feel the vibration. Okay? So there's two ways of doing it. Obviously, you have to move this line to the left by some amount, and that can be done by changing the natural frequency. For example, I can do it by increasing the mass, because remember, natural frequency is k over m. If I make m bigger, frequency becomes lower, goes to the left. Or if I make k smaller, the frequency, same thing, shifts to the left. So why don't we try to move it to the line 3 hertz? 3 hertz right there, okay? So we want to make natural frequency 3 hertz. In other words, right there at this location. So how can we do this? Well, remember that the frequency is given by this expression, okay? Now, if the mass is fixed, and we can change it, mass of the car, we can change the suspension stiffness, and if we want this thing to be 3, if you want this thing to be 3 as we want it here, this is intended to be 3, that purple one, then you work it out, you get k equal to this. And so by reducing the stiffness by 11%, you come up with a benefit that once the car hits that bump, the passenger will not even perceive the oscillation. Okay. Now, the problem is that there are some issues that are overly simplistic. We made the problem overly simplistic here. For example, we assume a single degree of freedom system. The car is not a single degree of freedom system, or if you use a more refined model, such as multi-degree of freedom system, you have more confidence. The second one is that uh, the thing is that we reduce the stiffness, okay? And that was beneficial for the sensation of vibration by the passenger. But if you reduce it to, if you make it out of gum, okay, then obviously it can't support its own static deflection or the weight of the car. Or you may decide to increase the mass, but that may not be possible because more mass means more fuel, etc. So that may not be feasible. Now, these are the range of oscillations for the range of frequencies and the displacement amplitude for different situations. This one is for the medical equipment, sophisticated medical equipment. For a tall building, the range of frequency is zero point 0.1 to 5 hertz, and the range of displacement amplitude is about 1 meter. Could be as order of magnitude being 1 meter or even more. And machine go between 10 and 1000 hertz, and roughly a fraction of a millimeter and centimeter, several centimeter, or the deflection amplitudes. Okay, displacement amplitude. Okay, now What's this business of vibration isolation? So first we covered the issue of a nomograph and using these charts to come up with a very rough, quick, acceptable, perhaps, solution based on the standards that are set by ISO. Now, there are different ways of controlling the vibration. One of them is to actually stop it at the source. In other words, by changing the mass or the stiffness of the structure, we change the natural frequency, and therefore, like the previous case, we moved the we moved that vertical line from 3.18 to the left. Okay, so that is trying to stop it at the source, but uh, it may be that that can't be done because, like in the previous example, uh, because the thing is already manufactured. You cannot do anything about it. The other one is isolate the source, and the isolation of the source is usually done by changing the stiffness and damping characteristics between the machine and the ground. Okay, so you put rubber pads there, or you put a spring there, and that is one way of uh, not being able to change it at the source, but at least trying to control it by isolating isolating the machine, the source of vibration, from the foundation or the ground. Okay, and this can be done if in the case of this can be done both uh, in terms of the displacement transmissibility and the force transmissibility. In other words, when you put these isolations in place, you basically either reduce the force through the foundation, or in the case of, for example, let's say the uh, base excitation, such as a car going over a rough road, you're trying to reduce the displacement transmissibility. So it can be done either at the displacement level or the force transmissibility level. Okay? And we have done things like this. We have done things like that in the first, I would say, the weeks 3 to 6, something like that. We have done force transmissibility and displacement transmissibility, etc. Now, the alternative is to do vibration absorber. So uh, this is at a, another approach to protecting a device from steady state harmonic disturbance uh, at a constant frequency. This is at a constant frequency is vibration absorber. Okay. Now, uh, the difference here is that you add things to the machine. You don't want to introduce rubber pads and springs there, but what you want to do is to alter somehow the machine in a way so that it solves the problem, alleviates the problem. Now, the problem, it's not the problem, but if you do this thing to analyze it, we may be going from a single degree of freedom into a 2 degree of freedom system, which has two natural frequencies, and obviously you have to stay away from them. We'll discuss this in the context of examples in a minute. Okay. Uh, so basically, the whole idea is to take the machine, add to it a mass, which is connected to the original machine through a spring perhaps, which has some stiffness, and instead of the machine vibrating violently or largely, it's the machine's vibration itself is reduced or completely eliminated, but at the cost of that added mass violently vibrating. Okay. Absorbers are often used on machines that run at constant speeds, such as sanders, compactors, reciprocating tools, and electric razors. So, I think it's instructive to go through this last instruction here. Probably the most visible variation of vibration absorbers can be seen on transmission lines. You may have seen transmission lines which something is hanging from it, like on the cables and telephone lines. Uh, you see that there is some gadget that's hanging there. It's a dumbbell-shaped thing, and that is a vibration absorber. Instead of the cables vibrating violently, the cables kind of stay put or reduce their vibration amplitude, but this dumbbell keeps vibrating in one way or other. The other example that I gave you is that skyscraper in Taipei, where on the top 5 or 6 floors of it, they have a gigantic ball hanging from the top of the skyscraper. So if there is any tendency of the building trying to sway and vibrate, that huge ball, steel ball, or huge ball on the top floor uh, prevents that by it vibrating and absorbing the potential vibration of the building itself. So here's the situation. We have a machine here. It's got legs, right? And this machine is, because of the nature of it, it could be, for example, an out of balance force, etc., out of balance machine turning here. And because of that, the actual platform vibrates violently. So what you do is you add a mass connected to the machine through a spring. And now we have, instead of a single degree of freedom model, we have a 2 degree of freedom model. And this vibration, I will show you that if this mass and the spring stiffness are chosen carefully, MA and KA are chosen carefully, then actually the displacement, the amplitude of the M becomes zero, okay? But this guy starts vibrating, okay? So we'll see that. First of all, the equation of motion is fairly straightforward. You should be able to do this to get this equation. It's very, very simple. For the final exam, you should be able to get equations like this based on free body diagram and mass acceleration diagram. The load is on mass 1. This is the mass 1, F0 sine omega t, and nothing on mass 2. So this is the equation of motion. All right. Now, because there is a sinusoidal force on the mass 1, everything, the steady state, everything will be vibrating at same frequency omega as the load. Okay, this is the stuff that we did in the last 3 weeks. Okay, so what I did, I took that, I took this thing, I took this and stuck it in there, differentiate this thing twice, differentiate this thing twice, stick it in there. So you're going to get uh, sine of omega 2, you just can cancel it out, and you get an algebraic equation. Okay, so actually it's this matrix times big XA equal to big F naught and 0. So it's an algebraic equation. And what you do to find the amplitude of vibration of the machine and the absorber, you just multiply both sides by the inverse of that, and the inverse of this is calculated right here. So just write this thing in detail. X is equal to this. So you take that vector, multiply it by that row, you get this thing times first component here, and you take this thing, multiply it by the second row, and clean it up, you get that. Okay, so this is the amplitude of vibration of the machine itself, and this is the amplitude of vibration of that absorber that you added later on. We don't know what Ka and Ma are. We have to design a system for that. So this is written in detail for you in one line. Instead of matrix expression, you wrote it like that. Now notice that if I make I choose Ka and Ma because I know omega. This omega is the frequency of the driving load. If I know omega and if I choose K and Ma so that this is 0, whoops, X is going to be 0. Big X is going to be 0. No, the machine will have no motion at all. This will have motion because if this is 0, this goes away and you get F naught over Ka. So that absorber will vibrate at an amplitude which is simply F naught over Ka, because this is 0, Ka here, they cancel each other out, this power, you get F naught over Ka. So the moral of the story is that if you make this thing zero, which means if you choose your Ka, that spring stiffness, and the mass value, mass of the absorber and the stiffness of the absorber spring, such that it's equal to omega squared. Now remember, we know omega. Then you know that the main machine doesn't move at all, but the absorber will move. Now, this is called this absorber parameters that satisfy this. They're for this particular frequency. That's why it's called the tuning condition. In other words, these things work when the frequency does not change. If you know the frequency of your machine, of your vibration, if you know that frequency, then this absorber works because you tune it. You tune the system. Select the Ka and Ma at the design stage so that it actually makes this thing zero. So it's a tuning condition uh, which works okay for machines or vibration systems that the frequency does not change a lot, and you know what that frequency is. Okay. Now, incidentally, I told you that if this is the case, uh, this term, big X becomes zero, and big XA simply becomes F naught over K with a minus sign, okay? So the actual motion of that absorber becomes this. It's the amplitude, big XA, which is this, times the sine omega t. Now, the other thing to notice is that if you take that displacement of the absorber and multiply it by the stiffness of the absorbing spring, if you do that, you're going to see that this is equal to minus Ft. So what happens is really the the applied load on the machine is nullified by the load coming from the spring because it's minus Ft, the spring meaning the one that you hung at the bottom of the machine. So, but that's why that thing does not move at all, because force on the top, Ft, force in the bottom, Ft, with a negative sign, and then cancel each other out. So there's going to be a zero net force acting on the primary mass. That machine original mass is called the primary mass. It does not move, and the motion is absorbed by the mass. Now, the good thing is that this thing that the machine, uh, that mass is vibrating at, that absorber mass is vibrating at, is not the that we are applying that is being applied to the absorbing mass is not the same as natural frequency of the system. Natural frequency of the system is a 2 degree of freedom system that you actually have to go and work it out. You'll see that the frequency is not going to be this. Okay. Uh, this is the frequency of vibration of that absorbing mass that you let it hung at the bottom of the machine, and this is not the same as natural frequency of the system. The two natural frequencies, that is, neither one of them is actually this in general. Okay. So I think I already mentioned this, but it's worth reading it again. The success of the vibration absorber discussed previously depends on several factors. First, the harmonic excitation must be well known. You have to know the frequency of uh, the your device, the loading frequency of your device, driving frequency, and not deviate from it much. Okay. Another key factor is the absorber design. In the absorber design, is that the absorber spring Ka must be capable of withstanding full force of excitation. In other words, notice that we know K over Ka over Ma is omega squared. Then you have a choice. You have to choose Ka and Ma. But if you choose Ka to be too soft, then it's going to cause a problem. Or if you choose MA to be too large, for example, then it's not going to fit underneath that table. So these are things that one should be careful about uh, because if you have your frequency omega, you have a choice. You have the freedom to choose Ka and Ma. All you need to do is Ka over Ma equal to omega squared. Omega is a known value. And this becomes a design problem. In other words, how do you choose the stiffness so that it actually is not too soft and doesn't fall apart here when the motion takes place? And the mass, how do you choose the mass so it's not too big, so that it's not bulky and it can fit in a very confined area, because you don't have that much of a space here. You have a very tiny space here probably that has to fit there. Now here's an example. We have a radial saw of a mass 73.16. So this is the mass of the entire machine. It has a harmonic motion because of the perhaps unbalance in the motor, and it's given at 180 RPM. So that's the operating frequency of the saw, and there is a force that's coming from the mass imbalance. Okay, so what we need to do is we need to design a vibration absorber at the mass here, at the spring here, so that it achieves an objective. We know the stiffness. We know the stiffness of the table legs. We need this. Okay, we need stiffness of that, and the maximum oscillation of the absorbing mass, okay, the maximum oscillation of the absorbing mass should not exceed this. In other words, XA, big XA must be zero point 0.2. So what do we know? Mass of the machine, stiffness of the legs, F naught we know, omega, the speed RPM of the saw we know is this. We want the table not to move, the actual machine not to move, and we want the the amplitude of the absorber mass to be 0.002, zero point 0.2 millimeter, 0.2 centimeter, which is 0.002 meter. So what we do is the question: what is Ka and what is Ma? Okay. Let me remind you, when we did this, we had two stiffnesses involved. I don't want to back up, but you can back up the video. When I started talking about the vibration absorber, there's two cases involved here. One is for the table, one is for the machine, which was called K1. That's really your K1. And the other one is for the absorber, which is K2, and we decided to call it Ka. Okay? So this is for the legs of the table on the machine. This is for that spring that we are trying to design it for. Omega squared is Ka over Ma. This is the tuning condition. We don't know what these things are. So the amplitude of the absorber mass is right here. So this is the motion of the mass, absorber mass, and we know that this XA, these are the same. We know that these are the same. Okay, that is what XA is, and we are told that XA is 0.002, so this is equal to 13 over Ka, and that will give us Ka equal to 6,500 Newton per meter. Now, if you go back to this equation right there, see that right there, we found Ka, okay, and we know omega to 6 pi. You plug it in, and you're going to get your absorber mass.